To accurately calculate the electrical load for kitchen equipment, it's essential to start with precise information. The initial data mentions 3.3 kilowatt ovens, a 1.20 kilowatt water heater, and a 3 kilowatt deep fryer. It also references Table 220.20, implying the use of a demand factor of 70%. However, the description notes the data is unclear and contains errors. Therefore, it is important to begin with the correct equipment ratings. Once the correct ratings are known, the process involves several key steps. Firstly, accurately identify all electrical loads. This includes not only the ovens, water heaters, and deep fryers, but also any other electrical equipment used in the kitchen, such as refrigerators, freezers, dishwashers, and lighting. For each piece of equipment, determine its rated power in kilowatts or watts. This information is typically found on the equipment's nameplate. Secondly, apply the appropriate demand factors. Demand factors are used to account for the fact that not all equipment will be operating at its maximum rated power simultaneously. Table 220.20 in the National Electrical Code, or NEC, provides demand factors for various types of kitchen equipment. The specific demand factor to use will depend on the type and number of appliances. For example, if you have multiple ovens, the NEC allows for a demand factor to be applied, recognizing that they are unlikely to all be running at full capacity at the same time. Similarly, a demand factor can be applied to water heaters and other appliances. It's crucial to consult the latest edition of the NEC for the most up-to-date demand factors and guidelines. Demand factors reduce the calculated load. Thirdly, calculate the total connected load. This is the sum of the rated power of all the electrical equipment. For each piece of equipment, multiply its rated power by its demand factor, and then add up all the results. This will give you the total demand load in kilowatts or watts. The formula is total demand load equals the sum of individual equipment loads multiplied by their respective demand factors. Fourthly, determine the feeder and service size. Once you have calculated the total demand load, you can use this information to determine the appropriate size of the electrical feeders in service. The feeders are the conductors that supply power to the kitchen equipment, and the service is the main electrical supply to the building. The size of the feeders in service must be sufficient to carry the total demand load without overloading. To determine the appropriate size, consult the NEC tables. For example, Table 310.15b16 provides ampacity ratings for various sizes of conductors. Select a conductor size that has an ampacity rating equal to or greater than the total demand load. Fifthly, consider voltage drop. Voltage drop is the decrease in voltage that occurs along a conductor due to its resistance. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The NEC recommends limiting voltage drop to no more than 3% for feeders and 5% for branch circuits. To calculate voltage drop, use the following formula: voltage drop equals 2 times K times I times D divided by Cm, where K is a constant that depends on the type of conductor, I is the current in amps, D is the one-way distance of the conductor in feet, and Cm is the circular mils of the conductor. If the calculated voltage drop exceeds the NEC limits, you will need to increase the size of the conductors. Sixthly, account for non-coincident loads. Non-coincident loads are loads that are unlikely to operate simultaneously. For example, a kitchen might have a large oven and a large water heater, but it is unlikely that both will be operating at their maximum power at the same time. In such cases, the NEC allows for a non-coincident load factor to be applied. This factor reduces the calculated load, recognizing that not all equipment will be operating simultaneously. Seventhly, verify the calculations. Once you have completed the calculations, it is essential to verify them to ensure that they are accurate. This can be done by using a software program or by having another qualified electrician review your work. It is essential to comply with the National Electrical Code, or NEC, to ensure electrical safety. The NEC provides detailed requirements for electrical installations, including wiring methods, overcurrent protection, and grounding. Ignoring these requirements can lead to serious electrical hazards. Here's a more detailed breakdown of each step. Firstly, accurate load identification. Gather precise information about each piece of equipment. This includes the rated power in kilowatts or watts, voltage, and any special operating characteristics. This data is usually found in the equipment's nameplate. For example, an oven might be rated at 3.3 kilowatts at 240 volts, while a water heater might be rated at 1.2 kilowatts at 120 volts. A deep fryer could be rated at 3 kilowatts at 208 volts. Secondly, demand factors from NEC Table 220.20. This table provides demand factors for various types of cooking equipment. For example, if you have multiple pieces of equipment, the demand factor might be less than 100%, reflecting that not all equipment will be operating at full capacity simultaneously. Note that the demand factors can vary depending on the number and type of appliances. For example, 2 ovens might have a demand factor of 80%, while 3 or more ovens might have a demand factor of 70%. Always consult the latest edition of the NEC for the most up-to-date values. Demand factors can be found in the relevant tables within the NEC. These tables provide specific percentages based on the number and type of appliances. For example, Table 220.20 gives demand factors for commercial cooking equipment. Thirdly, calculating total connected load. Once you have identified all the loads and their respective demand factors, calculate the total connected load. This is done by multiplying each load by its demand factor and summing the results. For example, if you have an oven rated at 3.3 kilowatts with a demand factor of 70%, the demand load for the oven would be 3.3 kilowatts times 0.70 equals 2.31 kilowatts. Repeat this calculation for each piece of equipment and then add up all the demand loads to get the total connected load. Total connected load equals load 1 times demand factor 1, plus load 2 times demand factor 2, and so on. Fourthly, feeder and service sizing. The feeder and service conductors must be sized to carry the total connected load safely. The NEC provides tables that specify the ampacity of different sizes of conductors. For example, Table 310.15b16 lists the ampacity of various conductors based on their size and insulation type. Select a conductor size that has an ampacity equal to or greater than the total connected load. For example, if the total connected load is 100 amps, you would need to select a conductor with an ampacity of at least 100 amps. The NEC also specifies requirements for overcurrent protection, such as circuit breakers and fuses. These devices are designed to protect the conductors from overheating and potentially causing a fire. The overcurrent protection device must be sized appropriately for the conductor and the load it is serving. Fifthly, voltage drop considerations. Excessive voltage drop can cause equipment to operate inefficiently or even malfunction. The NEC recommends limiting voltage drop to no more than 3% for feeders and 5% for branch circuits. To calculate voltage drop, you need to know the length of the conductor, the current flowing through it, and the conductor's resistance. Use the voltage drop formula to calculate the voltage drop and ensure it is within the NEC limit. If the voltage drop is too high, you will need to increase the size of the conductor. Voltage drop equals current times resistance, where resistance equals resistivity times length divided by area. Sixthly, non-coincident loads. In some cases, it may be possible to apply a non-coincident load factor to reduce the calculated load. This factor recognizes that not all equipment will be operating at its maximum power simultaneously. For example, a kitchen might have a large oven and a large water heater, but it is unlikely that both will be operating at full capacity at the same time. In such cases, the NEC allows for a non-coincident load factor to be applied. However, it is important to carefully consider the operating characteristics of the equipment before applying a non-coincident load factor. Seventhly, verification and compliance. Once you have completed the calculations, it is important to verify them to ensure that they are accurate. This can be done by using a software program or by having another qualified electrician review your work. Ensure that the electrical installation complies with all applicable codes and standards, including the NEC. This will help to ensure the safety and reliability of the electrical system. The NEC specifies requirements for wiring methods, grounding, bonding, and other aspects of electrical installations. By following these requirements, you can help to prevent electrical hazards. In the provided scenario, the initial calculation multiplies 32 kilowatts by 70%, resulting in 22.4 kilowatts. This approach might be valid if Table 220.20 specifies a 70% demand factor for the entire load. However, it is important to verify that this is the correct interpretation of the table and that all equipment is properly accounted for. It is essential to have accurate equipment ratings. Use the correct demand factors from the NEC. Calculate the total connected load accurately. Consider voltage drop. Ensure compliance with the NEC and overcurrent protection. Double-check all calculations. Remember, always consult the latest edition of the NEC and consider consulting with a qualified electrician to ensure the electrical installation is safe and compliant. Correct electrical load calculations are essential for safety and efficiency. Understanding the NEC and applying appropriate demand factors are key to accurate results. Always double-check the calculations and consult with a qualified electrician if needed. It is also important to consider future expansion when designing an electrical system. If you anticipate adding more equipment in the future, it is a good idea to size the feeders and service accordingly. This will help to avoid the need to upgrade the electrical system later on. Finally, it is important to keep accurate records of all electrical calculations and installations. This information can be helpful for future maintenance and troubleshooting. Keep a record of the equipment ratings, demand factors, conductor sizes, and overcurrent protection. This will make it easier to identify any problems and make necessary repairs. Also, remember to use certified equipment. Electrical equipment should be listed and labeled by a recognized testing laboratory such as Underwriters Laboratories or all. This indicates that the equipment has been tested and meets safety standards. Using certified equipment helps to ensure that the electrical system is safe and reliable. And proper grounding and bonding are crucial for electrical safety. Grounding provides a path for fault current to flow back to the source, which helps to trip the circuit breaker or fuse and prevent electrical shock. Bonding connects all metal parts of the electrical system together, which helps to equalize the voltage and reduce the risk of electrical shock. Follow the NEC requirements for grounding and bonding to ensure the electrical system is safe. Finally, perform regular maintenance on the electrical system. This includes inspecting wiring, connections, and equipment for any signs of damage or wear. Replace any damaged or worn components promptly. Regular maintenance can help to prevent electrical hazards and ensure the electrical system is operating safely and efficiently. By following these steps and guidelines, you can ensure that the electrical system for the kitchen equipment is safe, reliable, and compliant with the NEC. Always prioritize safety and consult with qualified professionals when needed. Additionally, it is important to consider energy efficiency when selecting electrical equipment. Look for equipment that is energy efficient and has a high Energy Star rating. Energy efficient equipment can save money on electricity bills and reduce the environmental impact. Also, consider using LED lighting in the kitchen. LED lights are much more energy efficient than traditional incandescent or fluorescent lights. They also have a longer lifespan, which can save money on replacement costs. Finally, be aware of electrical hazards in the kitchen. Water and electricity do not mix, so be careful when using electrical appliances near water. Never touch electrical cords or appliances with wet hands. Also, make sure that all electrical outlets are properly grounded. If you experience any electrical shocks or unusual electrical problems, contact a qualified electrician immediately. It's also good practice to provide training for employees on safe electrical practices in the kitchen. Employees should be trained on how to properly use electrical equipment and how to recognize and respond to electrical hazards. Training can help to prevent accidents and ensure a safe working environment. Always have a plan in place for electrical emergencies. Know where the main electrical disconnect is located and how to shut off the power in case of an emergency. Also, have a list of emergency contact numbers readily available, including the local fire department and a qualified electrician. Remember that safety is always the top priority when working with electricity. By following these guidelines and taking precautions, you can help to prevent electrical accidents and ensure a safe environment for yourself and others.